Hi, my name is Natalie Calvert, and this is Lab 4 Circuits. Introduction. The purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel circuits using multimeters to measure values and examine behavior of ohm resistors and capacitors. Some fundamentals are the conservation of energy and charge, Kirchhoff's circuit laws, node rule and loop rule, Ohm's law, capacitance, time dependence, and resistor capacitor. Some results that we had were the experimental value of RC was equal to 6.0168 seconds, and the expected value was 6 seconds. For our model, we used an online ideal model of a circuit to observe the interactions between capacitors, resistors, and multimeters in many ways. Some assumptions were that the resistance of wires is negligible, and the resistance of ammeter is also negligible. The change in voltage of capacitors plus the change in voltage in resistors should be equal to 0. For our first experiment, we did a series circuit. For the system, it was the circuit, and the surroundings were everything else. For the initial conditions, we had a circuit with two 1.5 volt batteries, two resistors, one 47 ohms and one 100 ohms, and two ammeters. We predicted that the current was equal in both ammeters from calculating the total resistance, this is from the node rule, and then taking the total voltage of 3 volts divided by that total resistance. That ended up being 0.02 amperes, and that was the actual reading, so we were correct. If turned around, the ammeter would just read the negative of our value, which was negative 0.02. When we replaced one ammeter with a voltmeter, it read 0 amperes and 3 volts. The ammeter reads 0 because the circuit is now open, which means that there is no current flowing, and the voltmeter reads 3 volts because the potential difference across openings is equal to that of the power source, which is the batteries. Continuing with the series circuit, when we closed the circuit and measured the potential difference across each segment, it gave us these values. We knew from the loop rule that this total should be equal to 0, and when we added up our values, it was in fact 0 volts. When we measured the current again, it was still 0.02 amperes, which is expected. And when you attach the voltmeter, it has a high resistance and small current flow, so the path of the current remains unaltered, therefore it is still 0.02 amperes. This is a graph showing the potential difference across different segments. As you can see, when it goes across the batteries, the slope increases quickly to 3 volts. Once it goes to the resistors, they get it back down to 0 volts following the loop rule. The 100 ohms resistor is clearly much steeper in slope than the 47 ohms due to it having more resistance. Continuing with the series circuit, when we connected the ammeter in parallel with a 100 ohms resistor, the reading increased to 0.06 amperes. This is because less current is encountering the 100 ohms resistor, and since the ammeter has 0 ohms, then the current increases in the ammeter. The process can be seen through the current equaling the potential difference divided by the resistance. For each area of the resistance, we calculated it by the potential difference divided by the current, as you can see below. For this next experiment, it involved an RC circuit. The initial conditions were we had a 10 ohm bulb, 20 ohm bulb, a 9 volt battery, and a 200 millifarad capacitor. When we first connected the battery to the 10 ohm bulb and the capacitor, the bulb starts out bright, then decreases until going out. This is slowly charging up the capacitor until the current is 0 amperes and it started out at maximum. When we disconnected the battery, the bulb again lights up, then slowly decreases in light until it goes out. The current is up, then drops to 0 amperes, while the capacitor is losing all its charge. To charge the 10 ohms bulb, it took about 10.9 seconds. To charge the 20 ohm bulb, it took about 18.2 seconds. To discharge the 10 ohm bulb, it took about 11.5 seconds. And to discharge the 20 ohms bulb, it took about 20.1 seconds. For this next part, we had a 9 volt battery, a 200 millifarad capacitor, and a 30 ohm bulb. I then took several readings of the potential difference as a function of time over the course of 20 seconds. We took these readings as the capacitor was slowly discharging. We found that the potential difference of the capacitor should change according to the first equation in the top right. When we linearized the data, we found the slope to be negative 0.1662 once the data was graphed and the line of best fit was found. This slope is equal to negative 1 over RC as seen in the equation. When solved, RC was equal to 6.0168 seconds. The expected value should have been resistance times capacitance. When that was done, we also got 6 seconds. For the comparison, our values that were calculated using the system in Excel were very similar to those of the expected value. Our calculated RC value was only off by about 0.0168 seconds. Some sources of error. Small errors could have been made, if any, because we used computer devices, which minimized our mistakes. I could have used the wrong calculations in certain areas, or the stopwatch times could have been slightly off. Discussion. What if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? If this was real life, the ammeter would have some resistance. This means that the readings for all of our current values would have likely decreased. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the current? If there was no resistor in the current, then our capacitor would get to this full charge almost right away since there is nothing hindering the current. This would not happen in real life because wires usually have at least a little resistance. It would charge up slower than expected in real life because of the resistance in the wires. Conclusion. The node and loop rules are important laws that can help us calculate different properties of a circuit. Voltage and current can easily change throughout the system, and these observations can be made by simply reading values. Voltage and current are different at points with capacitors and resistors and are time dependent as well. Thank you.